Okay, let's take a look at how to perform a chi-square goodness of fit test in Google Sheets/Excel. Now remember that a chi-square goodness of fit test is, in theory, literally all it's doing is it's comparing more than two proportions. So we've seen a simple one proportion test where we look at the proportion of a set of data and we compare it to a given value. Like we take a set of data and say, oh, okay, is the proportion of the students in my class who wear a baseball cap less than 25%? So now we're comparing the proportion of, baseball hat wearers to 25%. So that's comparing a sample proportion to a given value. And that value is always, a proportion, i.e. a percentage. And then we moved on and we did a two proportion test where we said, okay, let's look at the proportion of successes, right, whatever we deem a success in this sample, and compare it to the proportion in this other sample and see if there's a difference. Like, are the students in my stats class, is the proportion of students in my stats class who wear a baseball cap, less than the proportion of students in my algebra class? It's something silly like that. Well, now with a chi-square goodness of fit test, all we're doing is expanding that question from two sets of sample data to three or more. So we're basically saying, okay, I now have three or more sets of data, and I want to compare the proportions of successes, and you can't see me do air quotes around successes, in each of those sets. Now, the question could be comparing those proportions. I should say there's kind of two standard situations for a chi-square test. Either we have a situation like this question where we have a set expected proportion for all of the different groupings, right? So in this case, we have 1, 2, 3, 4, 5, 6 different groups, i.e. they're just colors of M&Ms. And we have this kind of pre-prescribed conception idea of the percentages of each color that should be in a bag. And you can see that they're not all the same. Now, that's one version of a chi-square test where we're looking for the proportions of all of our samples to match some other kind of distribution of proportions. The other version is we're looking for the proportions of all of our samples to be equal. So instead of saying, oh, there's 24 in this one, 13 in this one, 16 in that one, and so on and so forth, we would just take 100%, divide it by 6, right? So 100 divided by 6, and we would basically be looking for 16.67% in all of them, i.e. that they're evenly distributed. So those are the two kind of different versions of a chi-square test of goodness of fit. And it's really the same exact test. It's just sometimes we are given these kind of pre-prescribed distribution percentages, and then sometimes we're just looking for an equal distribution amongst all of our groups. Okay, so in this example, we've got M&Ms, right? We've got the 6 different colors. We have observed frequencies, i.e. the number of successes, right? The number of things that we counted. So we had 475 blue M&Ms in the bag and so on and so forth. Then we have these expected proportions, how many we think we should have. And then we're going to test whether or not they match at a 7% level. Now, as we know in probability, or sorry, in statistics and in probability, things rarely ever match, right? They almost never match perfectly. But what we're asking is, do they differ significantly enough that we can reject the null hypothesis that they do match, right? So the null hypothesis is always that the color, right, for all M&Ms is the same as the stated distribution, i.e., in general sense, it's whatever the success that we're looking for matches the distribution that we put forward. Either they're all the same or they match this pre-prescribed distribution. And then the alternative is always that at least one of them is significantly different, right? So the distribution of color for all M&Ms differs from the stated distribution. So that's a way of saying that just at least one of them is different. And that's kind of the two ways we'll normally state the alternative, is that it just differs in general or at least one of them is different. It's kind of saying the same thing, but when we say differs, some people think falsely that they all have to be different, and they don't. We just have to have at least one group, so in this case, at least one color that is significantly different than what we expect to see. And of course, if you think about it, if one is significantly different, at least one other is probably going to be different too, right? Because the probability or the distribution has to add up to 100%. So if one of them is 10% higher than it should be, then that 10% has to be made up somewhere. Now, it could be spread out amongst all the others, and then they're still quote unquote close enough. But you get the idea. But the bottom line is we need at least one to be significantly different. Okay, assumptions, right? So we always have qualitative data when we're doing chi-square because all we're doing is counting the number of successes, right? So in this case, we're counting each color, and you can see that color is qualitative data because all it's doing is describing the type of M&M we have. And we have one variable, i.e. color. Now you might think, don't we have 6 variables? No, we have 6 different choices for that one variable being color. So the number of variables we have is always kind of like the same thing as the number of questions you would ask, i.e. what color is your M&M? That's one question. That's one variable, but it has multiple answers. In this case, it has 6 possible answers. And then we have it from one sample, one big bag of M&Ms, right? One big batch of them. Okay, when we do chi-squares, we have to worry about independence of sampling. So we have to make sure that we're taking samples that are small enough that it's not going to change the relative percentages of each of these things. And we've seen this kind of assumption before, this kind of requirement before, that big capital N, the population, has to be greater than or equal to 20 times little n, which basically is a fancy way of saying our sample can't be any more than 5% of the total population. And we know there's a crap ton of M&Ms out there, so this is obviously going to be less than 5% of all M&Ms. And then all expected counts are at least 5. So remember in like binomials, we had, that n times p had to be bigger than 10 and all those kinds of, we kind of always have these minimum sizes of things, requirements. Well, this is the same idea, is that we need to make sure that all of our expected counts are at least 5%. Now up here, we don't have expected counts, we have expected proportions. But what we have to do is we have to take 24% of our total sample size and make sure that that's at least 5, and then do that for all of our proportions, all of our percentages. Okay, so let's check these assumptions. Right, so these numbers, as you can see, are not percentages because they're expected values, not expected percentages. Where did we get 624.48? Well, that's 24% of 2,602, and so on and so forth. So, for instance, orange is a really easy one to check. 20% of this, right? 10% would be 260.2 times 2. So there's our 520.4. So that's all those numbers are, is we're literally just taking, okay, if we think we're going to have 16% that are green, and we have a sample size of 2602, then we would have expected to see, what's that, green is the third one, we would have expected to see 416 greens when we actually saw 475. So, not perfect, but close-ish. And then we're going to check and see just how close all of those. Okay, so are all the expected values greater than or equal to 5? Well, heck yeah, they're all huge, right? They're all in the hundreds. And then no n is given, so we'll assume that n is greater than or equal to 52040. Well, where did this number come from? That's just this times 20, right? So we're basically just assuming that this is true, that big N is going to be bigger than little n times 20. So we can name the test, right? So this is our chi-square goodness of fit test. There's only two types of chi-squares that we're going to be dealing with. It's the goodness of fit and then the independence test, or sometimes called test for independence, same thing. Okay, goodness of fit is what we're doing. And here is our test statistic. We have to sum up a bunch of O minus E's squared divided by E. And this seems like kind of a relative frequency formula, and that's pretty much what it is, except for the square. And that's why our chi-square is always a right-tailed test, because it's always going to be positive, because when you square something, it's always positive. So you're always going to get values that get bigger and bigger and bigger. So you're looking for something that deviates way off to the right. So we're looking for a right-tailed test all the time. And all we're doing is taking each observed value and subtracting the expected from it, squaring that, and then divided by the expected. And in this case, they want us to set up what the first one would look like and what the last one would look like. So the first one would be, we're going to take our observed of 475 and compare it to our expected of 624.48. So that's where we get the 475 minus the 624.48. That's going to be squared, and then that's going to be divided by the 624.48. And then the last one is just going to be the last one, right? The same thing, 373 and 0.14. Sorry, 373 and the 364. So that's where we get the 373, the 364.28 divided by the 364.28. And then we would have to add all those up. Now, obviously, there's more than just the first and the last. So that's what the little ellipses here, the little three little dots means, is that we're continuing that pattern. And then that's going to give us the chi-square. Well, this is what we can do in Excel really easily, or Google Sheets. And I have mine set up here with a set of data that I had from a previous example. You'll notice that in this case, I've got a far many more groupings, right? I've got basically 16 different frequencies with expected frequencies. And in this question, I only have 6. So I need less. So I want to get rid of a bunch of these. And in order for my calculator to work, I just have to make sure that I only take out the middle stuff. You don't want to take out the first row or the last row, because all of these things are set up to count numbers within this range of rows. So it's looking at row 2 through row 17. If I shrink it down by getting rid of the stuff in between, it's still going to look at everything between this row and this row. They're just going to change, right? So when I highlight in the middle everything except for 6 of them, 2 on top and 4 on the bottom, and then go edit, delete those rows, you can see that this formula here is still summing E2 through E7 because it's only summing those numbers. So that's what we need. Okay, how does this work? Well, let's get rid of my data and put the new data in. And the new data is going to be observed and expected. So I'm just going to copy this all onto my page so I don't have to keep going back and forth. So I'll just put it over here. Now, these numbers need to go in this column. Here's a nice little trick. If you do Control-C and then click over here and do Paste Special Transposed, it takes a horizontal list and pastes it vertically. Now remember, these are not the numbers I want. I want the actual expected amounts, not percentages. So I have to create those. So it's going to equal this number, right, M29, times the total, 2602. oops, I used an 8 instead of a asterisk. 2602. And there is my expected value. I can drag this across and it will repeat that stuff. Okay, now I need to paste these over here. But the problem is if I try and do that, it's going to try and paste these formulas rather than these values. So I can start typing these in by hand, or I can do some fancy footwork with my stuff and do Control-C and then just put it in another place and do paste special values. And now the values are in each of these cells. You'll see up here that it's the value now instead of the, equals this times that. And then now if I copy those and go over here and do paste transpose, I know it's a multi-step process, but it keeps things more accurate than typing them in by hand where you could accidentally mistype something. And then all of this is pre-calculated for me, right? So these are all just differences. These are literally just O minus E. So there's A2 minus B2. And then I drug it down so that they're all doing the differences. And then these are just the difference squared. So it's literally just take what's in column C and square it. So that's why it's C2 squared. And then I drag that one down. And then this one is just take what's in the D column and divide by the expected, right? So there's D2 divided by B2, drug it all the way down, got all that stuff. And then the chi-square is literally just the sum of all of that. So this is just a simple summation of all of those. And that takes care of the chi-square value. Our degrees of freedom for a goodness of fit test is always number of categories minus 1. So in this case, we have 6 categories, right? 6 colors. 6 minus 1 is 5. So what I did is I used the count function for column A and then just subtracted 1 from it. And then the p-value is just the equals chi-square dot distribution dot right function, right? So chi-square dot dist dot right. And what you have to do is give it the chi-square value, right? So that's my E8, comma the degrees of freedom, so there's my E9, and then this gives you the corresponding p-value that goes with that chi-square. And you can see it's a really, really small amount because we had some big differences. I mean, look at this, 624 versus 475. That's a pretty big difference. Okay, down here I did it 2 different ways just to let you know that if you don't want to do this whole table thing, you can do it kind of a little bit easier by using the chi-square function. That's what this is, the chi-square function. And it's called the chi-test because we're doing a chi-square test. So equals chi-test. And then what you have to do is you have to give it the range of observed. So there's my A2 colon A7. And then comma the range of expected value. So there's my B2 to colon B7, and we're all good. Now the nice thing about this test is you wouldn't have had to have changed your how your data was represented. So for instance, I could have done equals chi test, right? And my observed range, I could highlight the horizontal things, and then comma, do the horizontal of the expected. And you see I get the same thing, a bunch of zeros. Then here, to also get the chi-square value. So when you do the chi-test, it's only going to give you the probability. It's going to give you the p-value associated with your test. It's going to give you the thing that you see that tells you whether or not you reject the null. And remember, you're comparing it to some significance level. In the case of this question, they wanted us to compare it to a 7% level. Our p-value is a lot smaller than 7%, so we were going to reject the null. But they're often going to ask you for the actual chi-square test statistic as well. And if you do the chi-test, it's just going to give you the p-value. Then you have to use the chi-square dot inverse dot right for right-tailed. So there's the function. And that's going to take our p-value and solve backwards for the test statistic that gets us that. So chi-square dot inverse dot right again, you have to give it some information. In this case, the first piece of information you give it is the p-value. So there's my E10, comma, degrees of freedom. And when you do that, you get the chi-square value, which you can see these two match. So you can do it either way. I kind of like the top way because it just kind of reminds me of how this thing is computed. But you can also go the nice, simple, easy way with the two functions of chi-test and chi-square.inverse.right for the right-tailed test. And then that would help you answer all the rest of the bits and pieces you would need, right? So here's the chi-square, that 51.88. Here's the p-value we got, which was just a bunch of zeros. Since it's less than or equal to the 7% that we set up for this question, we reject. Anytime we reject, there is significant evidence to conclude that the distribution of, well, what was our variable? Distribution of color, right, for all M&Ms, because we always put this back in terms of the population, so not our sample of M&Ms, but all M&Ms out there, right, differs from the stated distribution. So it's always going to be either it's the same or differs, right? The same is the null, so if we fail to reject the null, then it's going to be the same, and if we reject the null, it's going to differ. And that is how we do a goodness of fit test in Google Sheets.